In this lecture, we discuss the power method and various extensions. The power method is a technique for computing top eigenvalues and top eigenvectors of a symmetric matrix. So the problem we want to solve is as follows. Suppose we are given a symmetric matrix A, and I'll alternately describe it by writing this out, or just denoting it in the following way. We want to find its top and possibly bottom, but we discuss that later, eigenvalues and eigenvectors. We've seen several times in this class why we might want to do this. So this class is about a particular and very simple way to do this, called the power method, or sometimes called the power iteration. The algorithm is extremely simple, and it just says the following. As input, we start with our matrix A, and also some arbitrary vector Q of 0. And this is typically chosen to be randomly chosen. Then, for k equals 1, 2, after all, it's an iterative algorithm, we simply do the following. Z of k is equal to A times Q of k minus 1, and then Q of k is just the normalization event. Oops. So a key question is, first of all, why would we expect this to work? And secondly, how fast do we expect it to converge? As very often in linear algebra, we can get a good intuition by looking at diagonal matrices. So let's suppose that we have the simplest case of a symmetric matrix where A is actually diagonal. So let me just put down some numbers. 3, 2, 1. So what is its leading eigenvector? Well, clearly its leading eigenvector is the vector E1, 1, 0, 0, and it has corresponding eigenvalue 3. So let's see what happens. So again, our A is equal to this matrix, 3, 2, 1. Now what does a power iteration do? It picks some random initialization. So suppose we pick Q0, and of course this isn't random, but let's just for the sake of argument, let's see what happens. Let's suppose it's 1, 1, 1. Well, then Q of 1 is going to be the normalization of the vector Z of 1, where Z of 1 is just going to equal A Q of 0, or 3, 2, 1. Then what is Q of k going to be? It's going to be the normalized version of A to the k times Q of 0. And what is A to the k times Q of 0? It's going to be 3 to the k, 2 to the k, 1 to the k. And so you can see when we normalize this, this is very quickly going to go to the vector 1, 0, 0. So this is, roughly speaking, why we should expect it to work. And then the second question, how fast should we expect it to work? Well, we should expect that it has something to do with the largest eigenvalue divided by the second largest eigenvalue raised to the k, raised to the iteration, because that is how quickly this convergence will occur. So let's actually see this, the full details. The theorem we're going to prove says the following, and essentially matches the intuition that our simple diagonal example gave. I've rewritten the power method algorithm so you can see it. So it says the following. Suppose A is as above, in other words, it's an n by n symmetric matrix. And recall that by the spectral theorem, this means that we can diagonalize it via an orthogonal transformation, an orthogonal similarity transformation. So let's suppose that Q transpose AQ is a diagonal. I'll denote that by capital lambda. So this is the matrix that has the eigenvalues on the diagonal, and Q is a matrix whose rows are Q1 to Qn, and this is an orthonormal matrix. And the key assumption, which we see why the diagonal example gives the intuition for why this is necessary, let's also assume that the eigenvalues are ordered. And so what's the assumption here? The assumption is this inequality. So this strict inequality is the main assumption. Now, let cosine of theta k be given by the inner product between Q1 and Q of k. So let's pause here for a second and let's recall, what is Q1? So recall that given that Q orthogonalizes A, the columns of Q, i.e. the vectors Qi, are the eigenvalues, eigenvectors of A. So what is this? This is the inner product between, and therefore theta k is the angle between Q1, which is the true top eigenvector, with Q of k, which is our estimate of the top eigenvector after k iterations of the power method. So with these definitions, the algorithm, the theorem says the following, that as long as we don't start with something that's perfectly perpendicular to Q1, and if you go back to the diagonal example, you'll see why that would be no good, then the following is true. First of all, the sign of this angle subtended between the true top eigenvector and our estimate of the top eigenvector, the sign of that goes down at a geometric rate. So in particular, it has this dependence upon the initial angle, and again, we're assuming that this is not, that theta 0 has to be strictly less than 90 degrees. And here we see this dependence. So this is sometimes called the Eigen Gap. So in our previous example, the diagonal case, this was 2 over 3. And the bigger that is, the faster the convergence is. So here we see we have geometric convergence with rate lambda 2 over lambda 1. The bigger that gap, the better. And the second thing that this guarantees us is that our actual estimate for the eigenvalue, lambda k, converges very quickly to lambda 1. So lambda k minus lambda 1 is bounded by lambda 1 minus lambda n, essentially the whole breadth of the spectrum, times again a term relating to the tangent, times this, again, a similar rate in the decay, except now raised to the 2k. Okay? So the key points, again in summary, are first that initialization vector cannot be perpendicular to q1, and this will never happen as long as we choose the initialization vector q of 0, as long as we choose that randomly. And secondly, the second key point is that the convergence is linear, also called geometric. So from the definition of the iteration of the power method, we have that at the kth iteration, we're looking at a to the k times q of 0 normalized. So, going towards the first part of what the theorem guarantees us or promises us, what is sine theta k squared? Well, again, this is just by definition of sine. This is equal to 1 minus the inner product of q1 q of k squared. And so this is just the Pythagorean theorem. Plus the definition of sine. So check this if you don't remember it. So now let's plug in what q to the k is. Let's plug that in here. And we get that this is equal to 1 minus q1 transpose a to the k times q of 0 normalized. Okay, so far I've just been plugging in definitions. Now here's what I'm going to do, and this requires one of our key assumptions. So q of 0 is some element in Rn, and meanwhile q1, q2 up to qn is an orthonormal basis for Rn. Therefore I can always write q of 0 in terms of this basis. So let's do that. So q of 0 is equal to some scalar a1, q1, etc., all the way up to an, qn. And recall the key assumption that cosine of theta 0 is different from 0. This is basically equivalent to writing that a1 is different from 0. And I should add that because q of 0 is normalized, this is the same as writing that the sum of ai squared is equal to 1. Okay, so this is our key assumption. So now we can write down what a to the k times q0 is. I've got a to the k times q0 is just the sum of ai times a to the k times qi. But what's this? Recall that by definition, qi is an eigenvector for a. In other words, a times qi is equal to lambda I qi. And therefore, this is equal to the sum of ai times lambda I to the k times qi. So again, this is a summary of what we have. So what can we get now for sine theta k squared? This is just plugging in this definition. So plugging that into there, I get that this is 1 minus a1 squared lambda 1 to the 2k divided by sum of ai squared lambda I to the 2k. And now writing this, bringing the 1 into the fraction, this is just equal to sum from I equals 2 to n of ai squared lambda I to the 2k divided by the full sum. Sum of I equals 1 to n of ai squared lambda I to the 2k. And we can now bound this. So this is less than or equal to sum of I equals 2 to n of ai squared lambda I to the 2k divided by a1 squared lambda 1 to the 2k. So you see that I've made this bigger by making the denominator smaller. I've dropped some of these terms. This in turn is equal to 1 over a1 squared times the sum from I equals 2 up to n of ai squared times lambda I divided by lambda 1 to the 2k. And I can make this still bigger by replacing all the lambda i's with the biggest I from I equals 2 to n, which by assumption is equal to I equals 2. So this is less than or equal to 1 over a1 squared times lambda 2 over lambda 1 to the 2k times sum of ai squared, I equals 2 to n, but now we can use the identity that the sum of all of the ai's is equal to 1, so now this is just equal to 1 minus a1 squared divided by a1 squared times lambda 2 divided by lambda 1 to the 2k. And with a little bit of refreshing our trigonometry, we'll recognize that this is exactly equal to the tangent of the original angle squared. So we've got that this is equal to that. And remember, what did we start with? We started with sine theta squared. So this concludes the first part of the theorem, namely, the angle subtended after k iterations has a sign that's bounded above by tangent theta 0. This is just something having to do with the initial conditions, and then something that decays at a geometric rate. Okay. So this is the first part of the proof. So having concluded already that the eigenvectors converge, let's show now that the eigenvalues converge. Recall that our estimate at iteration k of the eigenvalue is just equal to q of k transpose a q of k. So this is natural, and we'll talk again why this would be the natural estimate corresponding to a vector q of k. So again, let's just plug in what q of k is. So q of k is just equal to a to the k times q of 0 divided by a to the k times q of 0. So therefore, expanding this out, we've got that lambda of k is equal to q of k times a q of k, which is just equal to q of 0 times a to the 2k plus 1 times q of 0. K came from the first k, another k's came from the second q, and then the plus 1 came from the from the original, from the A itself, and the normalization is just Q of 0, A to the 2k, Q of 0. And if we write this out with the exact expansion that we used on the previous page, this is now equal to the sum from 1 to n of ai squared lambda I to the 2k plus 1 divided by sum from I equals 1 to n of ai squared lambda I only to the 2k. So now let's see how far off this is from lambda 1. So lambda of k minus lambda 1, this is what we're asserting goes to 0, is just equal to, again just plugging in definitions and doing a little bit of algebra, the sum from I equals now 2 to n of ai squared lambda I to the 2k times lambda I minus lambda 1 divided by sum from I equals 1 to n of ai squared lambda I to the 2k. And it's easy to bound this above by lambda 1 minus lambda n times 1 over a1 squared times the sum from I equals 2 to n of ai squared times lambda I over lambda 1 to the 2k, which in turn is just bounded above by lambda 1 minus lambda n times tangent theta 0 squared. This is exactly the same calculation we did before and the same approximations, times lambda 2 over lambda 1 to the 2k. So this concludes the proof of the power method. There's a few interesting modifications or different versions of the power iteration. So we mentioned a few of those now. So one of these is called the inverse iteration. So the inverse iteration does the following. So it looks at the matrix. So it assumes that, so suppose we have already, by some other means, some lambda bar that's close to one of the eigenvalues, not necessarily the largest one, so any one that we want to estimate. So then what we can do is the following. If this is true, then that means that a minus lambda bar I inverse has a very large eigenvalue at lambda equals lambda I, and that's because this matrix is nearly ranked efficient. So the idea is to do power iteration using a minus lambda bar I, using this inverse matrix. Of course, this assumes that we can also, that not only do we know lambda bar, but that we also have a way of computing this inverse more efficiently than the original problem itself. Building off of this idea, there's something called the Rayleigh Quotient iteration. So we've already seen the Rayleigh Quotient, although we didn't call it this. So let's briefly discuss what this is. So again, for A, some symmetric matrix, we know that if x is an eigenvector, then ax is equal to lambda x. But what if x is not? Can we say that it corresponds to something like an approximate eigenvalue? This is exactly the notion of the Rayleigh quotient. So R of x is the approximate eigenvalue corresponding to any vector, not just an eigenvector x. So let's think about how we should define this. So if x is a true eigenvector, then we know that, as written above, ax equals lambda x, or another way to write this is that a minus lambda I times x, the norm of this is equal to 0. So the idea is let's let r of x, called the Rayleigh quotient, be what minimizes this value. So this is a convex function. So I'll leave this as an exercise. It's quite simple for you to show that this minimizing value is equal to x transpose ax divided by x transpose x. So this is, again, what's called the Rayleigh quotient. So how can we use this idea? We can combine this with the idea of the inverse iteration. And so the idea is the following. Instead of using every time we iterate and we get a new approximate eigenvector, well, then we use the inverse iteration with the corresponding approximate eigenvalue, or the Rayleigh quotient. Again, this requires essentially inverting a matrix over and over again. So it would only be useful in certain special cases. But in any case, here's the algorithm. So the input is starting point x0, that's normalized. So x0 is equal to 1. And then we iterate as follows. For k equals 0, 1, etc. Let's let mu k be our approximate eigenvalue corresponding to our approximate eigenvector. So in other words, the Rayleigh quotient of our current iterate. And then we have to now do a step of the inverse iteration, which is essentially equivalent to solving the linear system a minus mu k I zk plus 1 is equal to xk. You can see this basically means that I'm inverting a minus mu ki and multiplying xk by that. That's what zk plus 1 is equal to. And then finally just normalizing. So you zk plus 1 divided by the norm. So this is exactly the power iteration using a minus mu ki inverse. All of this has been about finding the top eigenvalue and the top eigenvector. So an important extension now is what if we want to find more eigenvectors or eigenvalues? So we can do this with a very simple extension of the power method called the orthogonal iteration. And before we describe exactly what this is, actually let me write down what this algorithm is, and then we'll see what the key step is. So this says for k equals 1, 2, etc., zk is equal to a times qk minus 1, and qk rk is equal to zk. So what this does is it produces an estimate, q0, q1, q2, etc., where each qi is an n by k orthogonal matrix. So you can see that if, oops, k is a bad choice here, n by m. So this will return m of the top singular vectors. So if m equals 1, check that this is just the power iteration. The key step that we need is what corresponds to normalizing and orthogonalizing, and that is this. So this step normalizes and orthogonalizes, and it's called a QR factorization. So I can just squeeze this into this page. So for a general matrix A, not necessarily square, n by m, what's called the QR factorization is writing A as a product of an orthogonal matrix and an upper triangular matrix. And that is the power method and a few of its natural extensions.